Hello, I'm Roland Larsson, and this video is about how to quantify surface topography or surface roughness. In a previous video, I discussed the phenomena of surface roughness. In this case, I will discuss how to get a number describing or different numbers, different quantities that describes how rough a surface is. I want to remind you that a surface, or surface roughness in general, is a multi-scale phenomena. So it contains form, the actual shape or form of a component. It has some waviness from the machining process. For example, it could be vibrations while turning, for example. And on top of the waviness, you have the roughness, and that's typically what is important for tribology or for wear, friction, and lubrication problems. But you also have roughness on the roughness, which may be also interesting for some lubrication problems, for example. Same goes if you make a kind of artificial surface with a texture. You do have roughness on that surface too, and of course roughness on that roughness. So this is important to remember. The roughness can be described on different scales, different amplitudes. So what you really have to do before studying roughness is to remove the form and the waviness. And in this example here, I have it's a gear tooth from a gearbox, and you can see here that you have the shape here is from the gear tooth shape itself, but on top of that you have some roughness here. You have some variations from that form. So there are different filters you can use here, but in this case I just found some kind of average line describing this form and the waviness, and I simply removed that form from the original primary profile, and you got a roughness profile. So this is what the typical stylus instrument is doing too. You get the primary profile and you use the filter and you get the roughness profile. So you can see that in some texts you can see that they talk about the P profile and the R profile. So this is what you really want to investigate if you are going to study or quantify the roughness itself. All right, let's move on then to see some typical values you can use here to quantify roughness. The most common one, I guess, is the RA value. That's the arithmetic average roughness height. So as you will see here, we will represent a typical surface with a profile like this. Remember now that this is a kind of exaggerated scaling in the vertical direction in comparison to the horizontal direction. The surface roughness or the asperities aren't this steep as they look like on this picture, but you really want to use an illustration like this because you want to show the roughness over a certain length. So, but remember, the slopes are only a few degrees, 1-2 degrees or something like that normally. So the RA value is simply the arithmetic average. So you actually take the absolute value and you integrate over the length L. And the length L is an important number to choose here. How long should L be? It depends on how well you have been doing the filtering. For example, if you have some form left in this, you will have a big influence of the form. So you have to use a suitable short L, but not too short, because you want to represent it. If it's too short, if you just have it from here to here, for example, you don't get a representative representative part of the profile. So that's something. There are standards about doing that, but you must keep that in mind when you do the measurement. You must compare it to the tribo contact you are also going to use here, the application you have in mind, of course. So you also need to, in this case, you have to find a mean line also. So in this case, you find a mean line which is having as much valleys as peaks, as much valleys below the mean line as peaks above the mean line. So what is RA then? RA is, as I said, it's maybe the most common number we're using, but is it the most useful number? No, I wouldn't say that. It's in this case we have two surfaces having the same RA, but you may have a kind of intuitive feeling about which one is better from a tribological point of view. I normally say to students that you should think about this as your bathroom rug. If you walk without shoes on this surface, which one do you want to walk on? Well, I guess you are going to choose the left-hand side surface here, because that will feel smoother than the right-hand side. So from a tribological point of view, RA has a pretty poor, the application of RA for tribology is really poor in a way. So here you have 6 different profiles having exactly the same RA value, and you can stop the video here now and think a few minutes which one of those surfaces will be the best one from a tribological point of view. Just stop it for a few minutes and then I'll be back after that. Okay, all 6 have the same RA value. Which one will be the best? Well, I would say that the best one is number D here. A little bit the same as the previous illustration when I talked about the bathroom rug. It's you have a lot of flat land in the top here, on the top surface here. So the surface carries a lot of load up here. If you compare it to the E1, which is the same surface but just flipped upside down, you can see it's much less area here to carry the load, so the pressure will be much higher up here than up here on this bigger part. This one will be poor, of course, because you will carry the load on peaks like this, and the pressure will be very much concentrated and on if you put this in contact with another surface, and you will have very high stresses and probably plastic deformation here. So the second best is probably the number A then. So because that also have a relatively big load carrying part in the peaks. There are a huge number of other roughness parameters. I think there are more than 100. If you have an equipment like an optical profilometer, you can get those parameters automatically, but I will mention a few of them here. So another average roughness parameter which is used relatively often is the RQ, which is the root mean square roughness. So instead of having the average arithmetic average, you have the root mean square. So mathematically it's defined like this. It gives you a similar number like the RA, but not exactly the same number. It's used in in lubrication. We use this number to compare it to the film thickness of the lubricant film. Coming back to that in videos about film formation in lubrication. Another more attractive parameter for tribology is the RMS slope. You actually try to find the average slope of the asperities instead of the average height. And the average slope is very interesting because the average slope tells you something about the contact mechanics. The steeper asperities you have, the higher the contact pressure will be. So RDQ, which is the parameter is named here, is a useful parameter. It's not used very much, I would say, but it's a useful parameter from a tribological point of view. Another set of parameters is around the amplitude density function, or the bearing ratio curve, or the Abbott curve. This one is used relatively much in industry, I would say. So if you have your roughness profile like this, you can get a probability curve. So it tells you a little bit about what's the probability to find a surface. Up here, there is 0 probability to find the surface. You come down here, and here eventually you touch the surface up here, then the probability starts to increase from 0 to something else. And around here, around the mean line, you have maybe the biggest probability, and then you go down through the profile, and eventually you find the lowest value, and below that there is no probability to find the surface anymore. So this is your amplitude density function, or the probability curve. If you integrate this curve, you find the cumulative distribution, and that curve is normally called the bearing ratio curve. So in this case, you can see this curve as if you have a plane moving through the profile, you can see how much up here you haven't covered anything of the profile. Down here you have covered 100% of the profile. So the shape of this curve tells you something. It tells you about the peakiness, for example, and how deep the valleys are. So the bearing ratio curve, or the Abbott curve, is used relatively often when you really need to define the surface roughness in a much better way. Then there are a number of surface roughness parameters defined from this bearing ratio curve. So you start by fitting a second to the bearing ratio curve. You find a second with a 40% length, and you find the smallest gradient, and then you draw a line through that second line, and then you can define a number of surface roughness parameters from that. For example, you have the core roughness depth, which is the slope or the height of this line from 0% to 100%. You have the RPK, which is the peak height. It tells you about how high are the peaks from the mean line, how high are they from the kind of the core roughness. And the same goes for the RVK, which is telling you about how deep are the valleys. And both these parameters are useful from a tribological point of view. Remember, the bathroom rug is the RPK tells you about how peaky the surface is and how comfortable it is to walk on it, while the RVK tells you a little bit about how much lubricant you may keep inside the profile and bring with you in the profile, which could be important. MR1 and MR2 are intersections of these curves, and they are sometimes used too, but I would say it's the RPK, RK, and RVK that are the most important parameters here. So they are used in industry very often. Another parameter used from time to time is the skewness. So if you have a Gaussian profile like this, normally distributed surface roughness profile, you have a probability curve that looks something like this. It's a have normal or Gaussian distribution around the mean line. But many tribological surfaces look like this. They are having a flatter top than the depth of the valleys. This could be a run-in surface that looks like this. Then you deform the peaks, highest peaks, and you flatten them out, and you automatically get a negative skewed profile. And that is what we call negative skewness. You see the mathematical expression here. Negatively skewed profile means that you have it's a little bit contradicting, but you have the highest probability to find the surface on the positive side of the mean line, while the opposite goes for a positively skewed profile like this. A positively skewed profile is, again, think about the bathroom rug. It's normally not a good tribological surface, at least if you want to have a low wear or friction. It could be low friction in some cases, but coming back to that in some of the videos. So skewness is kurtosis is another parameter. It is, I would say, not as often used as skewness, but it tells you a little bit of the peakiness of the profile. Again, starting with a Gaussian or normally distributed profile like this one, and then you have the kurtosis number. If you do the math here, you will find it's 3 then, kurtosis, the parameter. If you have a profile looking something like this, it has a lot of peaks and a lot of valleys. That means that there is a higher probability to find the surface around the mean line, and it's a lower chance to find it off the mean line, like up here or down here. Then the probability curve could look something like this, and then you get a kurtosis number that is bigger than 3. And on the other hand, if you have something like looking like this, and you get a probability curve looking like this, that you have a smaller chance, smaller probability to find a profile at the mean line, but higher probability to find it off the mean line, up here or down here. Then you have a kurtosis number smaller than 3, sometimes used. And if you take a look on this figure, which I found in a surface metrology handbook, you can see that there is a connection in between different types of manufacturing or surface finishing methods and the skewness and kurtosis number. So you can see here that the turning, for example, gives you a positive skewness from the beginning. You can understand that because you get something that looks like this. If I try to draw it here. But when you have been turning the surface and then you do the grinding of that surface, it will move from positive skewness to negative skewness. So here are a number of surfaces which are ground. And if you apply honing, honing is the same. You cut off the peaks and you get more and more negative honing. And you also get a bigger and bigger kurtosis. That means that you make more and more of the surface to come at around the mean line. So it becomes smoother and smoother also, you may say. So before talking more about the surface finishing methods and their connection to the parameters, I will also say a few words about the horizontal distribution of the topography. It's also important, especially in lubrication and elastohydrodynamic lubrication. In here I have a new gear surface profile. So you can see it's already from start. It has a kind of negative skewness. There are deep valleys, but not as high peaks. If you do a Fourier transform here, or you actually move from the from the profile to the frequency plane, and you see you plot the amplitude versus the wavelength. You can see that it contains, of course, a number of long wavelengths, but also a number of short wavelengths down here. And it is like that this, even if the amplitude of the short wavelength is much smaller than for the long waves, it may be that those ones are penetrating the oil film and create some wear or scuffing problems, because those ones are more easy to deform elastically than these ones, because these ones are sharper. The shorter wavelength means a sinusoidal wave which has a short wavelength and those then also high slope. So, but we will talk more about that in the elastohydrodynamic lubrication videos. As we discussed before in the surface roughness video, we measure with optical profilometry nowadays. So we actually get the three-dimensional map already from scratch. So we normally get 3D parameters instead of 2D parameters. And then we talk about S parameters. So instead of using RA, we use SA, and it's the same thing, but we are computing them or integrating these the mathematical expressions I showed you before. We integrate them all in both the X and the Y directions here. So it's more or less the same definition and they have the same meaning, even if you may not compare them directly with each other. So, and when you start making 3D parameters or definitions of parameters, you can find a pretty big number of surface topographies. So here I have two typical, or not typical, but two surfaces at least. This is a ground surface, which is a typical one, and this one is a chemically deburred, which is not a typical one. It's not a very common surface, I would say. But in both cases, the RA is around 0.4. But of course, again, from a tribological point of view, the behavior could be pretty different between these two. So nowadays, in most machines, most optical profilometers, you get a list of maybe 100 parameters, and the most common ones are those describing the height, the slope, the wavelengths. The connectedness is maybe not that common, but it tells you a little bit about if you have valleys, if they are connected or not. That could be important for a seal surface, for example. The number of peaks could be interesting. The summit radius is very interesting because, again, summit radius means if you have a big summit radius, you have a small slope. So that could be good from a tribological point of view. The number of valleys are sometimes important. It could be for seal surfaces, but could also be for gear surfaces maybe, and for engine, combustion engine cylinder liner surfaces. The lay is the direction of the grinding marks here. So the lay is in this direction, we normally say. So it's the direction of the grinding is important many times. So there is a long list of parameters here. I think they were called the Birmingham 14 or something like that in the beginning, and they were defined in the 80s, 90s. And this is a set that is more or less standardized nowadays. So you can take a look on these. If you want to learn more about them, you can find them on the internet normally. And as I already mentioned, there is no most useful parameter. We actually don't fully understand how the roughness influences the tribology. But So when you do an evaluation of a Tribo test, you normally measure those parameters before and after the test, and you compare, you see how they change, and from that you may draw some conclusions about what happened. But there is no single most useful parameter yet. A few words about also the surface finishing techniques and how they influence the parameters. Here you have 4 different types of surfaces: a ground surface, a cross ground, so you have 2 lays here, in both directions, and this one is shot peen. That means that you are kind of shooting particles on the surface, making indents that flattens it out in some parts. And this is a chemically deburred, which is a chemical kind of polishing or finishing method. And so you see that the appearance is very different, even if the RA could be the same in all 4 cases there. And if we now stick to the RA value for a while, even if I don't like the RA value for tribology, it still tells you about the smoothing and the surface finishing techniques capability to make smooth surfaces. You can see here that the primary processes creates relatively rough surfaces, but then you go on with grinding, honing, polishing, and lapping. You make it smoother and smoother, and lapping is a technique where you apply a abrasive, and you use it for lenses, optical lenses, for example, and they need to be very, very smooth and very plain also, because or planar, because they shouldn't affect the light wavelength. So you see here that here we are down to 0.4 micrometers or 0.05 micrometers. So it's 50 nanometers then. So it's very smooth surface. Depends also, again, on how long the L is in the measurement length. So that is about quantifying surface roughness. I hope you learned something about how to do that, and in later videos we will talk about how these numbers also are affecting, or how you use them in how to quantify the lubrication quality, for example. So thank you very much.